right, so we've kind of started chapter 7 and learned a little bit about the regression and a little bit about what kind of the object is and what we're trying to accomplish here. So we're going to start with how do we know when we can use a linear regression, and then we'll look at some other things we can discuss and things that we can learn from the regression. We are on page 3 on the lecture notes, and we finished chapter 2, or sorry, example 2 on the last video. And so conditions for using regression. So when can we use this? First of all, both variables need to be quantitative. This does not work with categorical variables. The straight enough condition, the scatter plot should have a straight pattern, at least more straight than curved. If there's a little bit of curve, maybe it can work, but it needs to kind of be in a borderline situation where, like, maybe it's straight, maybe it's curved, but it's not a good idea to have it get too curved. So hopefully the straighter the better. Outlier condition, outliers can dramatically influence the least squares line. We'll see some examples of this in the next chapter. And then the data should not become more spread out as we increase. So in other words, it should not start with a really strong relationship and then get wider as you go. It should be relatively consistent all the way through. So as long as those conditions are met, then we can look at scatter plots. So let's look at some of these, and we'll talk about the conditions in this case, plus some more interpretation that we talked about a little in the last video. So we have the age of a bridge and the safety score. So we can see, obviously, age is a quantitative variable, at least most of the time it's considered that. And then condition, that's some kind of rating scale. So that's going to be quantitative as well. Straight enough, there is no bend in this. No outliers. I mean, maybe that one, it's almost an outlier. But it also helps that, so it's not far from that point and that point. So it's not far from all of the data. If this one was up here way by itself, that might be a problem, but this scatter plot's a little bit spread out. So it's not super strong. So the potential outlier is not going to affect it as much as if it was a very strong scatter plot otherwise. And then we have the regression equation given here. So let's talk about this. So the correlation of negative 0.634. So the negative is indicated by it going down from left to right. And this just shows that as the age goes up, the condition tends to go down, which would make sense. Older bridges or anything else that is manufactured tends to lose quality as it ages. So older bridges tend to be less safe, as indicated by the negative in particular, which negative correlation, we're also going to have a negative slope. So negative 0.0196. So we talked about how to interpret these in the last video. Again, what we usually say, or what we're generally saying, is, so in this case, each year, the year is representing X. So as X goes up 1, the bridge safety score will go down because of the negative. And this is right at 0.02, but more precisely 0.0196 points. So down because of the negative, and then this would be your Y. Well, this is your V1, which is indicating that Y is going down by that much. I guess we could put Y here. So as X goes up 1, Y is going to go down by the slope. And then the y-intercept of 6.18 seems reasonable because we can see all the new bridges, which is the y-intercept again, is the interpretation of, or the value of y when x is 0. And so we're interpreting, in this case, if the age is 0, that means we're talking about a new bridge. And that kind of goes back to what we said in the last video. You want to kind of say these things natural. You don't have to say it in real mechanical, mathematical way, say it in a natural way. So a new bridge, and that would be when the age is 0, should have a score near the maximum of 7. And we can see that that's generally the case. If we're just along this, I guess we don't have any that are exactly 0. But we can see that seems reasonable that that'd be a good prediction of what the score would be on a new bridge. All right, so make sure you're comfortable with those, the interpretations. Again, the slope especially, you can kind of follow a pattern. As x goes up, y is going to go up or down by the slope. And then the y-intercept, when x is 0, y is going to be that value of the y-intercept. So get comfortable with those, and those get pretty easy to deal with. All right, so one way to tell if we can have a good regression model is, or if a regression model is good, I guess, a better way to say that, is looking at the residual scatter plot. And so what we have here, this is going back to the Burger King example that we looked at in the last time where we're comparing fat and protein. And so we still have protein along the x-axis. The original scatter plot had fat along the y-axis. Now we have residuals. So what this is doing is it's taking all the data points, it's taking the x value of the data point, which of course has a corresponding y value. And then we have a predicted y value, and it's calculating the residual. The residual, if you remember, is the observed y value minus the predicted y value. And so this is just calculating the residuals on all those data points and plotting them. And if you notice, we have the zeros right here in the middle. And that's just so that you can see how many have positive residuals, how many are negative. And what you want to see with this, as you can see from the points here, is basically nothing interesting, nothing that you would, if this is a regular scatter plot, you would say there's probably nothing we can really learn other than there's no relationship. And so anytime you're looking at a residual scatter plot, that's kind of what you want to see. You want to see just complete randomness. You want to see plenty that are negative and plenty that are positive. You want to see, 0 goes right through the middle, and then we're going to have the same kind of spacing above and below the 0 line. No bends. Hard to have outliers when you have no pattern at all, but no outliers, no identifiable pattern. And so when that is the case, that means that your regression model is going to be good. The regression line. So this is looking at a particular regression line. And that means that it's going to be a good one because you're over predicting some, you're under predicting some, and it'll balance itself out. All right, so then the residual standard deviation. And so this is just putting all those residuals on a histogram. And since the mean of the residuals is 0, the standard deviation is a measure of how small the residuals are. And so the closer all these are to 0, the better, because that would mean a very strong relationship and you're making accurate predictions or reasonably accurate predictions. So a good model will have the spread of the residuals consistent and small. And small, of course, is a relative number. If we're talking, our data points are from 10 to -10. Obviously, you don't want a spread of -40 to 40, but so it's a relative to the data. Histogram of the residuals helps us understand the residuals distribution. We can see, obviously, kind of like on the residual scatter plot, you want a lot of positives, you want a lot of negatives. And so then it should be fairly symmetric. And this is fairly symmetric. We have a little bit more on the positive side, maybe because that one's a little bit taller than that one. This one is a little bit taller than that one. So maybe a few more on the positive side, but not that big of a difference. And so that's what you want to see if you're doing a histogram of the residuals. All right, another indication of how good a model is we'll use R². So R, which is the correlation coefficient, measures the strength of the relationship. Closer it is to 1, the better. The closer it is to -1, the better. Closer to 0, the less the relationship is. And so R² R on the Burger King model was 0.762. If we square that number, we get R². And has 0.581. Now, why is it a capital R here and a lowercase r here? I actually don't know. And there's probably some reason for it, but I don't know that it's that important for what we're doing. But just know that that capital R squared is indeed the square of this lowercase r. So they are related just in that obvious way. And so what this means, what this 0.581 means is we can convert that to a percent, 58.1%. And so 51% of the variation in Y, which is fat, is due to the variation in protein, or X. And so what that tells us is how much is X actually affecting Y? And how much are they actually moving together, I guess. And maybe we shouldn't say affecting, because we're not looking at cause, we're just looking at relationship and correlation. But how much of that X, how much is X actually, moving with Y? And so if the R squared is close to 1, the regression line is useful. If it's close to 0, then it's not so useful. Obviously, it cannot be negative because we're squaring a number. So, all right, so looking back at the hurricane example we saw in the last video, R squared is 0.806. So that's very high. That's a lot higher than the Burger King example. And again, if we're throwing out an interpretation, 80.6% of the variability in maximum wind speed, which was the Y, is accounted for by the variation in central pressure, which was the X. So we're always stating the variability of Y is due to the variation of X. And you could probably state that, put the X first, and kind of say that in this case, the variation in pressure is accounting for 80.6% of the variation in Y, something like that. So it is possible, like you cannot just assume that the first variable is the Y and the second variable is the X, because you couldn't state it correctly and put the X first. But it's more important. Make sure you understand what we're saying here. We're saying that the variation in Y is due to the variation in X, or X is accounting for this much of the variation in Y. Okay, so that is it for this chapter. And the next chapter, we're going to look at a little bit more with just kind of some general ideas about regression. And there's no real math. I will post a video for the calculator, how to calculate a regression line. So you'll want to know how to do that. And you also want to know how to get the R and R squared to show up. And I'll go ahead and state that here. I can tell you how to do it without showing you. So before you do anything with the regression, and you could do this now, and then it'll be set up for when you need to do it. But on the graphing calculator, on the TI-84, TI-83, hit second 0. So second button at the top, 0 down, number 0 at the bottom. And that is your catalog. And so that brings up all of the commands that the calculator can do. So it starts with absolute value. I don't remember what's next, but all the A's and then all the B's and so on are in alphabetical order. And so what you want to do is, I don't remember, I don't have my calculator right here, but you can notice there are letters along, like each button has a letter. So it starts with A at the top, moves all the way down, you can see the letters. So wherever the D is, hit the D, wherever that D is, I don't remember where it is, but be near the top, or scroll to, and you'll have to scroll a little bit anyway, but at least if you hit the D, it'll take you all the way to the D, so you don't have to scroll through the ABCs. But scroll to diagnostic on, and then hit enter twice. And so when you do that, that will turn on the R and R squared. So now when you calculate a regression equation, which will be in a separate video, when you calculate the regression equation, it will also give you R and R squared. So we're not going to talk about, there is a formula for calculating R and R squared, but it's fairly tedious, and the calculator will do it for us. So let's just have it work that way. All right, so any questions, then feel free to shoot me an email.